Hello, everyone. Welcome to today's session. My name is Xiping. Now I'm studying for my doctorate in Nanjing University. My main research direction is automatic testing for AI software. I'm glad to be here to present our work on automatic speech recognition testing. Honestly speaking, it is the second time for me to give a presentation online at an international conference. I feel a little bit nervous, so I would like to apologize first if someone is not explained well during the presentation. Now let's come back. Our slides contain four parts. First, we talk about the background of our work. Then, we explain our approach. To validate the effectiveness of ASRTest, we apply it to four ASR models and one industrial ASR system with four widely used designs. Finally, we provide a brief summary. Automatic speech recognition systems aim to process a speech signal into a written format and obtain the information in human speech. The workflow of ASR can be molded into the process of identifying the input speech signal sequence as a textual token sequence. The token is the smallest output unit, and common types are phonemes, grapheme words. The combination of the acoustic model, pronunciation model, and the language model in conventional ASR systems can effectively eliminate the ambiguity of the result text. With a successful practice of end-to-end neural networks in machine translation and speech generation, end-to-end models have also been applied in ASR systems. They have exceeded the performance of traditional methods. All parameters of the end-to-end models are trained jointly rather than step by step. Compared with conventional ASR systems, end-to-end ASR systems employ one model to realize a mapping between the speech and the text. However, ASR systems could also suffer from defects and thus exhibit incorrect behaviors. While the quality and reliability of DN-driven ASR systems become critical for the end users, the nature of DN and application scenarios have made testing a challenging task. Unlike traditional software that relies on manually constructing the logic, DN adopts a data-driven programming paradigm and builds the internal logic with millions of parameters. This feature makes the conventional testing approaches no longer applicable for DN-driven ASR systems. Further, the physical deployment environment of ASR systems also contains variance interference factors. These factors may lead the practical impulse to shift out of training dataset distribution and thus make the ASR system behave unpredictably in the application scenarios. Thus, an existing testing practice that heavily depends on the manual collection of testing data under different application conditions become expensive as the number of testing conditions increases. To assure the quality of DN-driven ASR systems, researchers have proposed a few testing techniques in recent years. One is to use models based on neural networks. The most widely studied approach is features-based, in which a classifier is built using features generated from different sources to distinguish the correctly from the incorrectly recognized words. Therefore, the major contribution in ASR error detection and classification performance comes from recognizer-dependent features, which makes these approaches secretly related to the components of the ASR system used during the training process, and hence can't be generalized to other systems. Another representative work is based on differential testing methods. Their techniques address a oracle problem by utilizing a text-to-speech stranger that generates speeches from tests and then input these speeches into ASR systems for cross-referencing. However, these testing techniques lack proper guidance in the test case generation process, and they fail to consider the characteristics of practical application scenarios that limit their effectiveness in detecting erroneous behaviors. In order to alleviate these problems, our solution is to combine the ideas of fuzzing and magnified testing. We automate we automatically generate a large amount of input data based on existing speeches and construct a metamorphic relationship to find test case that violates the metamorphic relationship. Meanwhile, we employ gene impurity to guide test generation. Next, we introduce the design and the implementation of ASRTest, which aims to test DNA-driven ASR systems automatically and evaluate the performance of DNA-driven ASR systems in practical application scenarios. This figure in this slide presents the workflow of ASRTest. ASRTest implements a metamorphic relation that we define specifically for the ASR systems. ASRTest can generate new speeches based on the seed by applying transformation operators. During the process of speech transformation, it employs gene impurity to measure the uncertainty of the ASR model and the semantic preservation strategy to control the variance between the generated speech and the seed. Metamorphic testing is proposed to address the theoretical problem in test consideration. It can drive transformer tests from the successful ones and avoid the possible problems caused by the absence of test oracles through defining the metamorphic relation. MR is a necessary property of the target function or algorithm in relation to multiple inputs and their accepting outputs. Thus, the violation of MR indicates potential defects of software. Constructing a property MR is the basis for conducting the metamorphic testing. Intuitively, MR means that even if a perturbation or interference is added to the speech signal, the text information it contains has not changed, and the correct output of the ASR system shall not change. Currently, most of the practical application scenarios of ASR are consumer-centered. Therefore, ASR models increasingly need to be robust to human voices with different characteristics, various real-world noises, and other acoustic distorting conditions. Thus, we adopt three families of speech transformation operators in the implementation of ASRTest. By muting these voice characteristics, we can simulate the different speaker's voice and the manners of speaking to evaluate the speaker adaptability of ASR models. Noise injection refers to adding background noise to the speech. Noises injected by ASRTest are divided into white noise and environmental noise in different scenarios. Vibration simulation can make the speeches closer to the effect of distortion after being transmitted in the indoor air. To ensure the testing efficiency of ASRTest, we employ gene impurity to measure the possibility that generated tests can confuse the testing model. Deep Genie is used to evaluate the quality of tests for the classification DNA model based on the output of the softmax layer. The ASR model can be regarded as multi-category token classification model. The process of recognition is equivalent to outputting the token with the highest possibility several times. Therefore, based on the output of the softmax layer of the model, we can calculate the gene impurity corresponding to each token. In the ASR field, the token is the smallest output unit. Therefore, in order to reduce computation and improve testing efficiency, we convert the gene impurity of token to the gene impurity of word when using smaller units than words. In the whole guidance process, we were inspired by the evaluation metric of ASR performance. Speech recognition errors can be divided into three categories: inserting words that should not exist, and deleting and substituting words that should exist. The deleted words do not have corresponding tokens, so there is no corresponding gene impurity. Moreover, regardless of the value of word gene impurity, the inserted word is erroneous because it should not exist. Thus, both types of errors are directly related to the length of the token sequence and the gene impurity sequence. As shown in the slides, we use a number of words greater than the substitution threshold to estimate the number of substitution errors and the length difference of the gene sequence between the transformer test and the seed to estimate the number of deletion or insertion errors. Where the MR requires the seed and the transformer speech contain the same semantic information, the perturbation applied on the seed could increase the probability of triggering incorrect behaviors of ASR systems. Thus, one of the primary challenges for developing ASR tests is to balance the perturbation of speech signals and the preservation of semantic information. To this end, we propose a semantic preservation strategy to control the transformation process. We compare the spectrogram and the waveform of the seed and the transform test to measure the deformation degree of the transform test. Firstly, we measure the deformation of the spectrogram based on cosine similarity and the deformation of the waveform based on least square method. We define speech similarity as the average of two dimensions. If the similarity is below the threshold, we will use the same operator and reduce the degree of transformation by updating transformation parameters. ASRTest is designed to detect erroneous behaviors of DNN-driven ASR systems and help improve their performance. The DNN-driven AS model is a crucial module closely related to the performance of these systems. Therefore, we mainly explore the four research questions in this slide. We select four widely used datasets as seed sites. We experiment with four ASR models to alleviate the potential bias and assure the generality of the results. They are widely used in plenty of research and can represent the current advanced level of ASR. We set a conservative value range to generate variance parameters randomly. We also select the random strategy and neural coverage guidance as baselines. To be consistent with ASR tests, we retain high coverage tests and discard low coverage tests. We follow the convention of the ASR field and employ word error rate and word correct rate to evaluate the performance of ASR models. Figure in this slide presents the word error rates of different models on the tests generated by three guidance approaches. Obviously, the word error rates of all models on transform testing sites have increased more than the seed sites, but gene impurity guidance is more effective than baselines. This reveals that ASR tests can have higher testing efficiency by employing gene impurity guidance. Table shows the word correct rate of all testing models on the seed site and the transformer testing site. From the table, we can know that the valuable information about defects of the ASR model that can be feedback from the seeds is limited. In contrast, the word correct rate of all testing models decreased significantly on most transformer testing sites generated by ASRTest. We apply the speed transformation approach of ASRTest to generate retraining data based on the original training set. The number of transformer speeches for retraining accounted for about 10% of the original retraining data in our experiment. Table presents the word correct rate of all models after retraining with the transformer data generated by three generation approaches. As can be conjectured from the last table, the speed transformation approach of ASRTest can improve the performance of ASR models and is more effective than the other two approaches. In the case study, to evaluate the performance of ASRTest on industrial ASR systems, we apply it to the industrial system deep speech tool. It is developed by Baidu Research and has been widely applied in Baidu's related products. The experimental result confirms that ASRTest can still detect unaccepted outputs more effectively and can also make the industrial ASR system perform better in the face of different voice characteristics, various noises, and distorted speeches. In this paper, we propose the first green box testing approach for DNN-driven ASR systems and implement it into ASRTest. We design a mathematical relation specifically for the ASR system and implement three families of transformation operators to simulate practical application scenarios. Further, ASRTest adopts gene purity guidance during the test generation to improve the efficiency of detecting unaccepted behaviors. We employ four advanced ASR models for this site and an industrial ASR system to evaluate the performance of ASR test. The experimental results demonstrate that ASR tests can efficiently detect erroneous behaviors and effectively improve the performance of ASR models and industrial ASR systems. That's all for our presentation. Thanks again and good day.